Argon gas enters a well-insulated turbine at 1600 kilopascal and 450 degrees Celsius with a velocity of 55 meters per second and leaves at 150 kilopascal with a velocity of 150 meters per second. The inlet area of the turbine is 60 square centimeters. If the power output of the turbine is 190 kilowatts, determine the exit temperature of the argon. Let's begin this problem with the appropriate illustration. So, since we know we have a turbine, let's start with an illustration of a turbine. And let's note that state point 1 is going to be the inlet, and state point 2 is going to be the exit. We're told that it's a well-insulated turbine, so as it's well-insulated, then that means that there's no heat transfer, so we can just put Q dot equal to 0. Let's also illustrate the data that's being given to us. So the pressure at the inlet is 1600 kilopascals, and the temperature at the inlet is 450 degrees Celsius. We're also given the velocity at the inlet as 55 meters per second, and we're told that the exit, that the pressure is 150 kilopascals, and that the velocity, V2, is 150 meters per second. Additionally, we're given the inlet area, so A1 is 60 square centimeters, and if we multiply that by 10 to the minus fourth, then that's the same as 0.006 square meters. Now, we're also told that the power output is 190 kilowatts. So let's show a power output as W dot equals 190 kilowatts. Now note this is power output, so this is a positive term. And what we're trying to find then in this problem is the exit temperature T2 of the argon gas. So now let's look at the equations that are required for this problem. First of all, we're going to use the first law for a single stream steady flow process. So this tells us then that Q dot minus W dot equals M dot times the enthalpy change plus the kinetic energy change, V2 squared minus V1 squared over 2, and then plus the potential energy change, G Z2 minus Z1. Now in this particular problem, it's well insulated, so there's no heat transfer. We assume, like we do for all turbines, that the height change is minimal, so we'll just neglect the change in potential energy. And we'll also note that for gases like argon, since we don't have any thermodynamic property tables, we're just going to have to assume that argon is an ideal gas. So since it's an ideal gas, then that tells me that the enthalpy change is just equal to Cp times the temperature change. Now in this particular case, if we had Cp as a function of temperature, we could estimate the average temperature for the problem. Although we don't have the final temperature, we could still estimate and go into our property tables, table A2, and find the data. But we don't have any data for argon. So our only choice really is to assume that Cp is a constant at room temperature. So let's now just rewrite our first law. So we get minus W dot equals M dot, and then times Cp at room temperature times the temperature change T2 minus T1, and then plus the change in kinetic energy. Now, if we look at the data that's been given, we know V1 and V2, we know the power, we can look up Cp, we know T1, the only thing we don't know is T2 and the mass flow rate, and we can find the mass flow rate pretty easily simply by noting that M dot is equal to the velocity times the area over the specific volume. Now, we're given all the data at point 1, so let's find the mass flow rate based on our property data at the inlet. Another thing we might want to note is that since we again have no property data for our argon gas, let's just use our ideal gas equation of state, and therefore the specific volume is RT over P. Now again, we're trying to find the specific volume at 1, so we'll use our property data given at point 1 to get the specific volume. So now let's continue. We need to find the specific volume first. Let's go into our property tables, table A1, and look up the gas constant R. So the gas constant for argon gas, and this would be in table A1, is 0.2081. And this is going to be in kilojoules per kilogram per degree K. Now we can find the specific volume. Once we have the specific volume, we can find the mass flow rate, and once we have the mass flow rate, we plug all that back into the first law, and we can then solve for our only unknown, which is the temperature at the exit. All right, so let's do that. So V1 is RT1 over P1, so 0.2081 kilojoules per kilogram per degree K. We multiply that by the temperature T1 and then divide that by the pressure. So T1 is given to us in the problem statement. It's actually given to us in Celsius, so we're going to have to add 273 onto that. So we have 723 Kelvin. We always have to use the absolute temperature scale in the ideal gas equation. And then we divide by the pressure of 1600 kilopascals. Now, it appears to us that the units don't work out properly, but really they do. Keep in mind that a kilopascal is a kilonewton per square meter, a kilonewton meter is a kilojoule, so all the units are going to cancel out except for our volume units, so we get 0.09404 meters cubed per kilogram. Now we can find the mass flow rate. So if we plug in, again, we know the area and velocity. We plug in the data from above, and we get 3.509 kilograms per second. And now that we have the mass flow rate, now we can go back to our first law and solve. So we take our first law equation, and let's solve that. So we have minus the power. Please note that the power output is a positive term, but don't confuse that with the minus sign that needs to appear within the equation. So we have minus 190. Now the units are kilowatts, but a kilowatt is the same thing as a kilojoule per second, so let's just use those units. And then that equals the mass flow rate, so it's 3.509. CP is going to come from table A2 part A, so that's 0.5203 kilojoules per kilogram per degree Kelvin. We multiply this by the temperature difference, so we have T2 minus T1. Now we're just going to leave this in Celsius. After all, the temperature difference in Kelvin is the same as the temperature difference in Celsius, so it doesn't matter. If we're using Celsius here, then the end result is going to be in Celsius. All right, so minus, and then T2 minus T1. So here we have 150 meters per second squared minus 55 meters per second squared, and we divide it by 2, and we also have to divide by 1,000 to convert from meters squared per second squared into kilojoules per kilogram. And now all the units should work out properly. I should have put kilograms per second over here in the mass gas flow rate term. So there's only a single unknown. If we go through the mathematics, we end up with T2 equals 327 degrees Celsius.